Hello everyone, and thank you for joining us on this webinar entitled Using Automated SDN and NFV Infrastructure to Provide Security, Agility and Insight in the Cloud. My name is Daniel Joseph Barry and I'm the VP of Positioning and Chief Evangelist in Napatech. And I'm going to be walking you through some of the challenges that cloud service providers are facing today and how SDN and NFV could be used to address some of those challenges and what you need from an NFV infrastructure in order to enable service agility, security, and insight. So to start off with, I'd like to take a look at how cloud service demands have been evolving over the last number of years. I'm looking at two different reports here, one from 451 Advisors and the other from RightScale. But when we think of cloud services, we often tend to think of infrastructure as a service or infrastructure hosting as the common service that you would expect. But as you can see here from the figure from the survey that 451 Advisor performed in 2005, you can see that end users are expecting a lot more from the cloud service providers than just infrastructure hosting now. They're expecting managed services, application hosting, and security services as well. So it'd be fair to say that infrastructure as a service is becoming commoditized and that enterprises are expecting a lot more than just cost savings from their cloud service providers. Now, one of the things driving this is the fact that enterprises have overcome their initial skepticism with regard to cloud service performance and security and are now actually beginning to move business critical services to the cloud as well. And as you move business critical service to the cloud, obviously your demands for how those cloud services are performing increase and your demands on the cloud service provider itself increases. This has been captured very well in that report from this quote down here, which says that increasingly users are demanding that their cloud service providers deliver enterprise-ready, value-added, easily scaled services with security baked deeply within. And the hallmarks of cloud now are speed and agility, but most of all, services. Some of the key words here are, of course, security, speed, and agility. So these are going to be determining the winners from the losers going forward. Now, the other report that I'm quoting here is the 2017 State of the Cloud report by RightScale, which showed that the vast majority of their respondents were using cloud services, but 2/3 of those were adopting a hybrid cloud strategy approach. So we're not going to see a step change here where everybody moves from their traditional on-premises data centers to cloud services. There's going to be a sort of transition where we'll have leaders and laggards here, where they're going to be using a combination of public, private, and also their traditional on-prem type of solutions. So you have to be able to encompass all of those different types of needs going forward. But security, speed, and agility are still going to be important no matter what kind of cloud strategy that you're going to be adopting. Now, one area, just to use an example of where there's been an evolution and how cloud service providers and data center hosting providers have responded, is in the area of internet connectivity. So up to now, we've seen that most of the services that have been moved to the cloud are services like email or CRM type of solutions, which could easily be accommodated by public internet connectivity. So if you're an enterprise with a number of different branches, it's quite easy to allow your branches to access those cloud service providers over the public internet. But as you start moving more demanding applications into the cloud, then things like delay or latency or jitter for that matter start to make a difference. So then the public internet connectivity is no longer good enough because the experience that your users are having are going to be more demanding. So the cloud service providers have been responding to this, and nearly all cloud service providers now have a best performance direct connectivity type of solution. So Amazon Web Services have Direct Connect, Google have Cloud Interconnect, and Microsoft Azure have ExpressRoute, just to name a few examples in this regard. And these are great because they will provide a better connectivity for the different branches to the cloud services that they need. And typically in enterprises, there will be several different cloud services that they are using. But the headache for the IT department is that they have to maintain these connections to each of the branches for each of the different cloud services that they are supporting. And that's obviously an operational challenge every day, but also it's a challenge when you try to add a new location, an example of which we'll look at in a moment, just to see what's involved when you do that. So data center hosting providers have responded to this particular need by offering what, and I'm using the term here that was coined by Equinix, our cloud exchange services, which are basically interconnect services that will allow enterprises to connect to the data center hosting provider, and he would take responsibility then for connecting onwards to the different cloud services that are involved. So I mentioned Equinix came up with the term cloud exchange, but Digital Realty also has their service exchange concept, and CoreSite has an open cloud exchange service as well. So the basic premise here is that the data center hosting providers would already be hosting many of the cloud services that the enterprise would use in their various locations around the world. So when you have a branch that needs to access that cloud service, it's more than likely it's within the walls of that data center that's been operated by that particular operator. So rather than having to make a connection to all the different cloud services from the different branches, you can just ensure you have a connection to the data center through their cloud exchange, and they would take care of the rest either within the data center or between their data centers. So obviously this makes it a lot easier on the IT organization in the enterprises, makes their management of the entire situation a lot easier, and it also helps them when they try to add new locations, as we'll see in a moment. Now, obviously, to make this work, there has to be a certain amount of cooperation between the cloud service providers, the data center operators, and the telecom service providers, who would probably own the last mile connection to each of those branches. But I think we also have to recognize here there's a certain dynamic going on between these different actors in the industry. All three of them will be busy forging alliances and partnerships to provide complete solutions for enterprises. And all three would also like to be the preferred service provider to the enterprise in helping them make that transition to the cloud. What could determine the winner in this particular co-opetition situation is the entity that provides the best security, agility, and insight into what is happening for the enterprise's services once they move to the cloud. So let's take an example of an enterprise that needs to add a new location very quickly. So this could be another different geographic region where you have to ensure that the employees in that particular region get access to all the cloud services that are supported by that particular enterprise. Now, what that means is that the cloud service provider and the data center hosting provider and the telecom carrier need to respond very quickly to this demand and be able to scale the services that are required to support the new data load that's going to be coming from this branch, that they can ensure that the cloud services that are required are closely located so that they can meet the different performance parameters that are required here, and that the connectivity is established to that particular location, all in a very dynamic and automated fashion, so that it's done as quickly and efficiently as possible. And security, of course, has to be baked in, not just in the connection, but also in the actual services themselves. So this is quite a demanding process, but the more you can automate that process and make it easy, the more you're going to be preferred by the different enterprises as the particular partner of choice. Now, SDN and NFV are interesting in this regard because they provide a conceptual framework to automate this process. So the ability to provide management and orchestration of establishing these services, making the connectivity, etc., is extremely appealing. But there have been challenges in implementing SDN and NFV, and some of those are related to the management and orchestration, and some of them are actually related to the infrastructure. So we're going to take a look at those right now. So up until recently, management and orchestration was a bit of a headache for the NFV community because there didn't seem to be any consensus in how to implement management and orchestration and what needed to be involved. It was pretty clear from the outset that you needed to have some sort of common framework that everyone could agree on, because all these different actors would need to cooperate in order to provide a service to the enterprise. So in 2017, the MEF published their Lifecycle Service Orchestration Framework, and that's been receiving very broad acceptance in the community as a framework that everyone can get behind and use in order to establish their management and orchestration solutions. What it consists of is different layers, from a technology domain perspective to a service orchestration perspective, right up to supporting the different third network services that are required. And the framework is designed really to address the challenge of automating, managing, and orchestrating services, not just within the domain of a particular carrier or cloud service provider, but also between these different entities through open APIs. So you have these network level orchestration open APIs, which would be technology domain specific, like NFV or SD-WAN or Cloud Exchange in this example. And then you'd have service level orchestration open APIs, which would be providing some of those fundamental functions that you need in order to provide a service, such as fulfillment, control, performance, assurance, policy, usage, security, and analytics. And these would need to be coordinated, of course, on an end-to-end level between the different operators that will be involved in delivering that service to the end user. Now, this is a framework that is not just theoretical, it's also complemented by some real solutions that are using this framework as a starting point. So some of those are the ONAP, which is an amalgamation of the OpenO and AT&T's eComp initiative in the Linux Foundation. And the other is OpenMANO from Etsy, which is a competing management and orchestration implementation. But they both would adhere to some of these framework ideas, which are coordinated with other SDN and NFV initiatives in Open Daylight and Open NFV, as well as Etsy. So there is a broad acceptance of this coming forward, and it actually coming at a very good time, because this now allows many organizations to see how they can start to build that service agility and service automation into their SDN and NFV frameworks. But automating the services using the management and orchestration is only good if you can also automate the NFV infrastructure itself. In order to automate that, you have to some sort of insights into what is happening. Now that insight is essential for the actual orchestration of the NFV infrastructure, but it's also essential for implementing some of that security and agility we talked about earlier as being essential for cloud services. So what this insight does for you is it provides info on what is happening in the network and which resources are available. And so that allows you to start optimizing how the resources are being used and deployed, and be able to take action before something becomes an issue in the network. But what it also allows you to do is to actually see what is happening in the network and react to it. So you can start to recognize from a security point of view anomalous behavior and start to act to contain that potential threat by rerouting traffic or isolating traffic, or even just blocking traffic. So these are all different policies that you can implement now, but what it requires is that insight into what is going on in the network. And of course, it also provides you with that agility that you need to deploy and scale virtual functions and connectivity on demand. So by knowing what you've got available, by knowing which kind of routes you can establish through the network, then you can actually know where you can deploy new functions, when you have to actually scale those functions, and when you may have to just move those functions in order to optimize how those are being used. So the combination of insight, security, and agility are all the things that we can see are important to actually delivering those cloud services in the way that enterprise need. So automated NFV infrastructure is absolutely essential to providing the service agility and meeting some of those end user demands going forward. So building an automated NFV infrastructure is the foundation of making all this work. And if you look at the timeline and where we are right now in establishing that automated NFV infrastructure and enabling that service agility, security, and insight, we are probably in the middle of that process right now. So there's been a number of different challenges, and here we're highlighting 5 steps related to 5 particular challenges that you have when developing automated NFV infrastructure. I'm going to walk you through this timeline here and show what's happening at each one of these steps, the challenges that are there, and what the potential solutions are that are already being worked on right now in order to address these different challenges and provide that automated NFV infrastructure to support service agility, security, and insight. So the very first step that was taken on this journey was just to get data delivery to work with flexibility. And the very first solution to this was the Intel Open Network Platform, which provided a standard server with a standard NIC as the common hardware platform that could be used throughout the data center, complemented by an open hypervisor and virtual switch, say KVM and OVS, and using here also DBDK as an API of the different virtual functions. Now, the beauty of this solution here is that it actually allowed that vision for NFV to be established. You had that common hardware platform that was deployed throughout and could be reused. The open hypervisor and virtual switch abstracted that hardware then from the software, so that allowed any function to be deployed anywhere and moved anywhere and scaled on demand. The only issue with this solution, because it was based on standard servers and standard NICs, is that it suffered some throughput performance issues and the CPU core consumption that was required in order to make the virtual switching work to support the kind of speeds and rates and capacities that are required in telecom networks was just not acceptable. So great conceptually, but performance and CPU core costs were an issue. Just to put it in perspective, for many of these solutions here to run at 10 gig and above, you would probably be using more cores handling the data than you would actually hosting virtual functions, which of course is not acceptable. Now, the solution to that was to use technologies like SR-IOV. So this is something that's supported by most standard NICs out there. And what it does essentially is it bypasses the open hypervisor and virtual switch and actually delivers data directly to the virtual functions memory space. Now that works. It provides you with good performance, and you're not using a lot of CPU cores to do it. In fact, you're using a minimal number of CPU cores in order to do this. The problem with it, though, is that it actually removes that virtualization layer that's abstracting the software from the hardware. So now your software is directly tied to not just the standard server, but the actual NIC that's used in the server. And many of the implementations of SR-IOV on these different NICs were slightly different. So not only would you be tied to a specific to an SR-IOV NIC, but you'd be also tied to a specific vendor of an SR-IOV NIC. And I think the best quote for this has been delivered by Martin Taylor, the CTO of Metaswitch, who said that SR-IOV works, but it's clunky. You're bypassing the software that makes the cloud cloudy. And this is the concern. One of the issues here you have is that when you may be solving a CAPEX problem here because you're reducing the number of CPU cores that need to be used and you're improving performance, but you're introducing an operational problem. Operational costs are 10 times more, 10 times larger than you would have with CAPEX in this regard. So you would definitely have an issue, and it's been proven by many that have tried to go down this path, of using these kind of solutions to efficiently manage and orchestrate end-to-end services based on this approach. So many people are looking for a different approach to this, which could combine some of the advantages of step one, the Intel Open Network Platform, with some of the flexibility and ease of operation that you have with that, with the performance and cost efficiency of this particular solution. So that is one of the things that needs to be addressed in step 3. So we need to not only just have performance and cost efficiency, we also need to have that flexibility to be able to deploy virtual functions anywhere and then be able to move them on demand or scale them as required. So that requires that the accelerated open hypervisor and virtual switch are in there again as an abstraction layer to these virtual functions. So the hardware and software are abstracted from each other. But one of the approaches to solving this is one that Napatech has been looking at for the last couple of years, which is to find different mechanisms to accelerate the performance of the virtual switches in this environment. So we went back to the Intel Open Network Platform, this step 1, as a starting point and try to see how we could improve upon that. And one of the ways we can improve upon that is to actually replace the standard NIC as delivered with the standard server with a NIC that's designed specifically for NFV. And this NIC will allow a more efficient delivery of data through OVS and DPDK to the virtual functions. And what we've been able to achieve by this approach is we were able to enable automation on this common hardware platform with full theoretical 40 gig delivery to the virtual function using just one CPU core. So this is something that we've proven now, and that it's able to do this, actually delivering 60 million packets per second. That's full theoretical 40 gig using 70% of one CPU core. So that's a breakthrough, because now we've been able to combine the performance, flexibility, and cost efficiency that we're looking at step 1 and step 2 in order to make the delivery of data and virtual switching work in the NFV infrastructure. So that's a vital step in reaching our goal. So the solution that we've used is the Napatech NFV NIC, and that is an FPGA-based SmartNIC, which we've designed specifically for virtualized environments. So what do we mean by that? Well, first of all, we designed it for flexibility. So we're able to support multiple speed rates on the same hardware. And as you can see here, that's everything from 10 gig all the way up to 100 gig. And the reason we can do that is because the logic of the actual port, the port logic here is defined on the FPGA itself. So in order to support a different speed rate, you would use a different FPGA image. And it's very easy to exchange one FPGA image for another. So, and you can even do it remotely and on the fly. So this is a solution that can allow you to actually extend the lifetime of your hardware. But because we're based on an FPGA, it's not only the characteristics like speed rates that we can increase, or the capacity for that matter, but we can also start adding other functionalities or other types of solutions on there. So one of the solutions that we're looking at is OVS acceleration, but it could also be hardware acceleration and other types of solutions that you can actually place on the same FPGA image and reuse the hardware to do other things. So that's one of the design principles that we've had from the beginning for this particular solution. Now, we've also designed it for performance. So we wanted to have full theoretical performance in there. So the pipeline itself is designed for 200 gig capacity with 0 packet loss. And we've also designed it for good performance from a latency point of view. So we've been able to measure it's between 50 and 100 microsecond port to VNF round trip latency using this particular piece of hardware. Now, it's designed for reconfigurability and to be able to do that remotely and on the fly. So you can actually update the speed, you can update the capabilities by downloading a new FPGA image onto the FPGA itself. This is just a piece of software that you can load onto the FPGA there. And you can do that remotely. You don't have to go out and actually go to the hardware itself. It can all be done remotely. And there are fallback mechanisms here so that if the update of the FPGA doesn't work, it can actually fall back to the previous FPGA software version. So you have minimal downtime, and you have also fallback assurance. So you have minimal risk when you're doing this as well. So an extremely powerful solution, which actually we can leverage when we start looking at the next step in the 5 steps of addressing the NFV automation, which is extending the performance improvements that we have, both technical and cost wise, to other functions and other challenges in the NFV infrastructure. So up to now, we've been talking about the OVS acceleration because it's been an essential part of getting NFV infrastructure to work properly. But you also have the issue, of course, of having to manage your cost as the data load is increasing in your data center over time. So this is a fact that we all know. We can introduce a solution in year 0, let's say OVS acceleration, which will dramatically reduce the cost. But we know that that cost will increase again as data loads increase. So you have to have some other mechanisms then to be able to keep your cost under control and keep your cost per bit under control. And the only way you can do that really, if your data capacities are increasing, is to get more out of the infrastructure that's already installed. And there you can actually leverage FPGA-based SmartNICS because these allow you to actually add new capabilities, new capacities, etc., using the same hardware. So as I said previously, the basic pipeline of the FPGA SmartNIC solution that we've made can handle up to 200 gig, but you don't need to start with that. So you can start with a 10 gig, 25 gig, or 40 gig solution, and then as the data load increases, you can start upgrading to new port speeds and remotely upgrade the same piece of hardware to support higher port speeds without actually changing any of the physical hardware. But if you take that a step further, there's other things that you can do which are even more interesting, which is hardware acceleration of compute-intensive data processing functions. So there are functions out there like encryption and compression, which are going to be more and more important as more of the traffic is getting encrypted and more of the traffic needs to be compressed before it's stored in the storage networks. So the ability to actually take some of these compute-intensive data processing functions and run them on an FPGA is very, very attractive. This is because these functions are not well suited to software running on a CPU. They tend to be quite inefficient, but they're ideal for platforms like FPGAs. So you can see some significant improvements in performance if you can offload these functions onto a hardware accelerated platform like an FPGA. So what we've built in Napatech in order to enable this is a framework where we can have some of the functionality like our OVS acceleration functionality coexisting with custom IP blocks, intellectual property blocks that will be implementing a specific hardware acceleration function. So if you look at the FPGA image on the NFV NIC, about 70% of that image is still available for custom IP, even when we are implementing the OVS acceleration solution. So you have the possibility there of dropping in using a partial reconfiguration type of approach, a custom intellectual property block that could be based on an independent third-party IP block vendor, or even an IP block that's been developed by the customer themselves, which is implementing some of their secret sauce or their algorithms that they need to keep secret. And the framework is built in a way that the existing logic, which would be supporting the OVS acceleration solution, would not be affected by any of the new IP that's being introduced onto the NFV NIC itself. So there's an isolation between these two environments, which is very important. So examples of the kind of IP blocks that could be placed on this NIC would be encryption decryption blocks, compression blocks, or transcoding blocks for video or for radio transcoding. So these are all examples of what can be done. To give a more concrete example, we can look at a case where Napatech was working together with Nokia on a proof of concept solution that would allow a file for files to be compressed at a rate of 40 gigabits per second. The challenge that Nokia was facing at the time was that it needed to compress these files before they were put into storage, and needed to do that at a rate of 40 gigabits per second. But using software on the CPU as a way to do the compression, it just wasn't efficient. And typically a CPU core would be capable of compressing at a rate of 1 gigabit per second. So in order to do 40 gigabit per second compression, you would need to parallelize this job across 40 different CPU cores in order to make it work. And that's more cores than were available in the particular server that was in question here. So this was not an option. So looking at hardware acceleration, the proof of concept was to see if using FPGA technology you could do that in a more efficient way, and we proved that it could be done. What we did was we built a solution where there was a compression IP on the NFV NIC, and that was capable of doing 40 gigabits per second compression in real time, and be able to place a gzip header on the file when it was being sent back. We needed an application that would consume one CPU core that would be able to send the files to the FPGA for compression and then receive the files back and then store them in the storage area network. And that was the entire solution. So if you look at it from that perspective, we were able to provide the same solution using just one CPU core for the application that was managing the process, instead of 40 CPU cores that would have been required to do software compression. But beyond that, we were also able to show that you could reduce the average compression time by a factor of 30 compared to software without compromising on the compression ratio, which in this case was around 2.5 or 2.6 to 1. So all in all, an extremely powerful solution that showed a significant reduction in the number of CPU cores that you would have, and actually, to be honest, made a compression or some of possible in an NFV infrastructure. So this is just an example here, but we've also seen encryption examples which would follow some of the same kind of performance metrics. So 1 gigabit per second encryption or decryption is possible using a single CPU core. So again, if you need to provide that kind of facility at 40 gigabits per second, you would need 40 cores. This again can be provided on an FPGA using just one CPU core to manage the process. So again, a 40 times improvement there. So these are the kind of improvements that you can get from some of these intensive functions when they start to get offloaded onto FPGAs. Which brings us to step 5. So now we've got our virtual infrastructure to work. Our virtual switching is working with performance, using as few CPU cores as possible without compromising flexibility. We've been able to take some of those functions which are a little bit more demanding, like encryption and compression, and accelerate them on the same hardware. So now we're ready to start tackling the challenge of providing insight into virtual traffic, which to date has been a major challenge to do properly. The issue involved in trying to see particularly east-west traffic, that is traffic between virtual instances that doesn't go out onto the physical network, is that you would need, the only way you can see that traffic today is actually to provide a span port or a tap on the virtual switch itself. You have to remember here the virtual switch is running in software. So if you're using 10 CPU cores to run your virtual switch, to turn on the span port would actually require that you would copy all of the traffic that the virtual switch is seeing in software, which means in effect that you have to go from 10 CPU cores to 20 CPU cores, or doubling on the number of CPU cores in there. And that would mean that you're using almost half the server just for doing that. And that's not acceptable. So definitely people are looking for a different way in order to provide this kind of insight. So we can take advantage here of the implementation of the NFV NIC, because the OVS acceleration solution that we're providing actually gets insight into all the traffic, not just the north-south traffic, but also the east-west traffic. So you have the possibility of actually replicating all that traffic on the FPGA itself, which is much more cost efficient, doesn't cost any CPU cores, and allows you then to provide a span port functionality from the NFV NIC that can deliver a copy of the traffic that's going across the virtual switch to the virtual probe that might be on the same server, or even out to a physical probe or appliance on the physical network. So with this basic capability now, you have the option of sending this copy traffic in different directions. So what that means, if we just take the example of a virtual probe, what that allows you to do is to be able to deploy functions, then spin up a virtual probe so you can monitor the activity, the east-west traffic, for example, and then use that insight then to inform the management and orchestration layer of what's going on, so they can make decisions on how to optimize the deployment of these virtual functions and to scale these functions as they see that the demands are increasing. So this is the kind of insight and automation that's possible once you have this capability in place. So now that we've seen the different solutions that you can have in order to implement all these different steps towards a automated NFV, we can now make service orchestration possible. And the key step was step 5, really providing insight into what is happening on a very efficient NFV infrastructure. Because now you're providing the insight into those service orchestration functions, the fulfillment, control, performance, and also the security that's very important in this. So this could be from virtual probes, it could be from physical probes, it could be from security, virtual security appliances, or even physical security appliances that are getting that insight from the tap functionality or the span port functionality that we built into the NFV NIC. So this is what really will make the service agility work in the management and orchestration layer. And with that in place, then you're able to offer that cloud service connectivity with agility and built-in security that the end users are demanding. So to finish off, I just wanted to provide you with a last slide, talking about the NFV NIC and reiterating some of those solutions that we just looked at, which are actually making that 5-step process possible, and which is actually able to drive the automated NFV infrastructure and also the insight to drive the management and service orchestration that you need to have with service agility and security. So one of the solutions that we've been able to provide on this is the virtual switch acceleration solution, where we've been able to deliver with 40 gig to a virtual machine using just a single CPU core without the need for solutions like SR-IOV, which is extremely attractive. We've also been able to show that we can have custom hardware acceleration, so you can drop IP blocks onto that same NFV NIC for encryption or compression or transcoding, and that could be third-party IP blocks or customer IP blocks. And we've also talked about the ability to have a span port on here, so you can take advantage of the fact that we're able to replicate the east-west traffic on the card and be able to drive insights through virtual appliances, virtual probes, or even physical probes and appliances for security or network management optimization purposes. So these are the different solutions that we have. And if you want to understand a little bit more, please visit us at napatech.com for more information, or just contact me, Daniel Joseph Barry, at djb@napatech.com. Thanks very much for your time, and I hope to hear from you very soon.